Picture this. It's the year 2035, and humanity stands on the threshold of becoming a multi-planetary species. Our robotic emissaries have been exploring Mars for decades, sending back breathtaking images and invaluable data that have transformed our understanding of what it means to be a planet in our solar system. The first crewed missions are launching with increasing frequency, carrying with them not just astronauts, but the dreams, hopes, and desperate survival instincts of our entire species as we face mounting challenges on our home world. Infrastructure is being planned with meticulous precision, habitats designed to withstand the harshest conditions known to human experience. And the first permanent settlements are taking shape on engineering drawing boards across the world. From NASA's Johnson Space Center to SpaceX's Starbase facility to the European Space Agency's technical centers across the continent. But then, something changes. Something that threatens to unravel decades of careful planning. Billions of dollars in investment. And the accumulated wisdom of humanity's greatest minds working toward our cosmic future. A cosmic visitor, designated 3I/Atlas in our speculative scenario, begins its inexorable approach toward the inner solar system. And with it comes a cascade of potential threats that could fundamentally alter our relationship with the red planet forever. This isn't just a minor course correction in humanity's space program. This is a potential existential challenge to our species' expansion beyond Earth. This isn't science fiction crafted from pure imagination. This is science speculation, grounded in real physics, real orbital mechanics, real atmospheric dynamics, and very real consequences that could affect every human being alive today and every generation that follows. Today, we're going to explore what happens when two worlds collide, not physically in some catastrophic impact scenario, but in terms of human ambition, meeting cosmic reality head-on. We're going to examine how a single interstellar visitor could potentially derail humanity's greatest adventure, and what that might mean for our future as a spacefaring civilization that spans multiple worlds. The story we're about to unfold touches on some of the most fundamental questions of our time, questions that will define the next century of human existence. How fragile are our carefully constructed plans for space exploration when faced with the dynamic, unpredictable nature of the universe itself? What happens when the cosmos throws us a curveball we didn't see coming? Despite all our sophisticated detection systems and predictive models. And perhaps most importantly, how do we balance our dreams of cosmic expansion with the harsh realities of celestial mechanics, orbital dynamics, and the fundamental forces that govern motion in space? As you settle in for this comprehensive journey through speculative science and very real possibilities, imagine yourself as a mission planner at NASA, ESA, SpaceX, or any of the dozens of organizations working toward human settlement of Mars. Every decision you make affects not just robotic missions worth hundreds of millions of dollars, not just the careers and reputations of brilliant scientists and engineers, but potentially the future trajectory of human civilization itself. The weight of that responsibility is something that keeps real scientists and engineers awake at night, staring at trajectory calculations and orbital mechanics equations. And today, you'll understand exactly why that burden feels so heavy. The engineering marvels taking shape in preparation for these missions are staggering in their complexity and ambition. Consider the Mars Base Alpha project, currently in advanced development phases at multiple international space agencies, which will serve as humanity's first permanent foothold on another world. This isn't just a research station or temporary outpost. It's designed to be a self-sustaining city that could eventually house thousands of people, complete with manufacturing facilities, agricultural systems, power generation infrastructure, and even entertainment and cultural centers that will make Mars feel like a second home rather than an alien frontier. The technological challenges involved in creating such a settlement are almost incomprehensible. Every kilogram of material that reaches Mars costs tens of thousands of dollars to transport from Earth, which means that Mars Base Alpha must be designed around the principle of maximum self-sufficiency. 3D printing systems will manufacture everything from replacement parts to construction materials using Martian regolith and atmospheric gases. Closed-loop life support systems will recycle air, water, and even waste products with efficiency levels that exceed 99%. Because on Mars, there are no second chances and no margin for waste. The year 2019 marked a true turning point in our understanding of interstellar visitors when astronomers using the Crimean Astrophysical Observatory detected what would become the first confirmed interstellar comet to visit our solar system. Initially catalogued with the mundane designation C/2019 Q4, this cosmic wanderer was later renamed 2I Borisov, acknowledging both its extraordinary interstellar origin and its discoverer, amateur astronomer Gennady Borisov, whose dedication to skywatching had uncovered something that professional astronomers with billion-dollar telescopes had missed. But what captured the scientific community's attention and sparked intense international collaboration wasn't just that we had identified another visitor from beyond our solar system. It was how much we suddenly realized we still didn't know about these mysterious travelers and how unprepared we were for their implications. The detection of 2I Borisov came just 2 years after the discovery of 1I Oumuamua, the first confirmed interstellar object to visit our solar system. Together, these discoveries revolutionized our understanding of how common such visitors might be, and forced us to confront the reality that our solar system is not the isolated, predictable environment we once believed it to be. Instead, we live in a dynamic cosmic neighborhood where objects from other star systems regularly pass through, carrying with them the potential to disrupt our carefully laid plans for space exploration. The implications of discovering these interstellar visitors extend far beyond their immediate scientific value. Each object carries with it a chemical signature that tells the story of its home stellar system, isotope ratios that reveal the nuclear processes that forged its atoms, mineral compositions that hint at the planetary formation processes that occurred around distant stars, and organic compounds that might provide clues about the distribution of life-building materials throughout the galaxy. When we study these cosmic refugees, we're essentially conducting astronomy at the molecular level, using individual atoms and molecules as messengers from stellar systems so distant that their light takes years or decades to reach us. Fast forward to our speculative scenario, and we encounter 3I Atlas, a hypothetical third interstellar visitor that represents everything we fear and fascinate about these cosmic nomads. Unlike its predecessors, which passed through our solar system relatively harmlessly, 3I Atlas arrives with a trajectory and timing that brings it uncomfortably close to Mars during what mission planners consider the most critical period in human space exploration history. This isn't just bad timing, it's a convergence of cosmic mechanics and human ambition that could redefine our relationship with space exploration for generations to come. But before we dive deep into the potentially catastrophic implications of this cosmic encounter, we need to establish a comprehensive understanding of the two main characters in our unfolding drama. Mars, the world we're desperately trying to reach and colonize before potential global catastrophes make Earth uninhabitable. And 3I Atlas, the mysterious visitor that might change everything about how and when we achieve our multi-planetary future. Mars has captivated human imagination for millennia, appearing in our night sky as a brilliant red beacon that seems to pulse with mysterious energy, almost as if it's trying to communicate with us across the vast emptiness of interplanetary space. The ancient Greeks called it Ares, after their god of war, whose unpredictable temperament and violent nature seemed to match the planet's variable brightness and distinctly blood-red appearance. The Romans named it Mars after their own war deity, and that martial association has persisted through centuries of human culture, influencing everything from science fiction, literature, to modern mission. Names like NASA's Mars Reconnaissance Orbiter and the European Space Agency's Mars Express. But the Mars we know today through decades of sophisticated scientific exploration is far more nuanced, complex, and fascinating than any ancient mythology could have imagined. It's a world that simultaneously offers humanity's best hope for expansion beyond Earth, and presents challenges so severe that they push human technology and endurance to their absolute limits. The cultural impact of Mars on human civilization cannot be overstated. From the earliest astronomical observations by ancient civilizations to the science fiction masterpieces of the 20th century, Mars has served as humanity's canvas for projecting our hopes, fears, and dreams about life beyond Earth. The planet has inspired countless works of literature, art, music, and film, each generation reimagining Mars through the lens of contemporary scientific understanding and cultural anxieties. The atmospheric dynamics of Mars create weather patterns and phenomena that are both familiar and utterly alien to Earth-based experience. Dust devils, some reaching heights of several miles, dance across the Martian plains with a frequency and intensity that dwarfs their terrestrial counterparts. These towering whirlwinds are driven by the extreme temperature differentials between the planet's surface and its thin atmosphere, creating convection patterns that can lift millions of tons of fine dust into the upper atmosphere, where it can remain suspended for months, gradually settling back to the surface in patterns that reshape the planet's appearance over geological time. This alien atmosphere, composed primarily of carbon dioxide at 95.3%, with traces of nitrogen at 2.7%, argon at 1.6%, and minute quantities of oxygen, water vapor, and other gases, is less than 1% as thick as Earth's atmosphere. To put this in perspective, the atmospheric pressure on Mars is roughly equivalent to what you'd experience at an altitude of about 22 miles above Earth's surface, well into what we consider the edge of space. This extreme thinness creates an environment where liquid water cannot exist stably on the surface under most conditions, where temperature swings can be extreme and rapid, and where protection from cosmic radiation becomes a critical survival requirement. The ground beneath your feet would tell an epic story of planetary evolution spanning billions of years, a narrative written in stone, dust, and the geological features that have been shaped by forces both familiar and utterly alien to Earth-based experience. Mars is approximately half the size of Earth, with a diameter of about 4,220 miles compared to Earth's 7,926 miles. This smaller size translates to significant differences in fundamental planetary characteristics that affect everything from gravity to magnetic field strength to atmospheric retention. The reduced size means that Mars has only about 11% of Earth's mass, resulting in a surface gravity that's roughly 38% of what you experience every day on Earth. If you weigh 150 pounds on our home planet, you'd weigh only about 57 pounds on Mars, a fact that sounds exciting and liberating until you begin to consider the long-term implications for human physiology. Prolonged exposure to reduced gravity causes bone density loss, muscle atrophy, cardiovascular deconditioning, and a host of other physiological changes that could make it difficult or impossible for Mars colonists to ever return to Earth's higher gravity environment. Today, as we stand on the verge of actually reaching Mars, we carry with us millennia of accumulated mythology, scientific speculation, and artistic vision that will inevitably influence how we perceive and interact with the red planet, standing on the surface of Mars. If you could somehow survive without a spacesuit for just a moment, which you absolutely could not, you'd find yourself in an environment that's both alien and strangely familiar, like stepping into a landscape painted by an artist who understood Earth's geography but decided to reimagine it under entirely different physical laws. The sky above you wouldn't be the brilliant blue of Earth that we take for granted, but rather a butterscotch hue during the day, created by iron oxide dust particles suspended in the thin atmosphere. This dust gives Mars its distinctive reddish appearance when viewed from Earth, but up close, the color palette is much more subtle and varied, ranging from deep russets to pale yellows depending on lighting conditions and atmospheric clarity. As the Martian day progresses towards sunset, you'd witness one of the most beautiful and otherworldly sights in our solar system. The sky would fade to deeper blue-green tones near the horizon as light scatters through the thin atmosphere in ways that create color combinations impossible on Earth. The Sun itself would appear about 2/3 the size it does from Earth, due to Mars's greater distance from our star, and sunset would come with a distinctive blue halo around the solar disk, a phenomenon that has been captured in stunning detail by Mars rovers and continues to amaze scientists who study atmospheric optics. But size isn't the only fundamental difference that matters crucially for our story and for human survival on Mars. The red planet orbits the Sun at an average distance of about 142 million miles, compared to Earth's 93 million miles. This greater distance from our solar system's energy source means that Mars receives only about 43% of the solar energy that Earth does, contributing to average temperatures that hover around -80 degrees Fahrenheit. Even during summer at the equator, temperatures might reach a relatively balmy 70 degrees Fahrenheit during the warmest part of the day, but winter at the poles plunges to a bone-chilling -195 degrees Fahrenheit, cold enough to freeze carbon dioxide out of the atmosphere into solid dry ice. These extreme temperature variations are made even more dramatic and unpredictable by Mars's elliptical orbit and axial tilt. Like Earth, Mars experiences seasons due to its 25-degree axial tilt, but these seasons last about twice as long, because a Martian year equals 687 Earth days. When you combine this extended seasonal cycle with Mars's more elliptical orbit compared to Earth's nearly circular path around the Sun, you get a world where the southern hemisphere experiences much more extreme seasonal variations than the northern hemisphere. During southern summer, Mars reaches its closest approach to the Sun, creating intense heating that can trigger planet-wide dust storms lasting for months and covering the entire globe. These dust storms aren't just weather events. They're planetary phenomena that can shut down solar-powered equipment, strand rovers and landers, and potentially trap human settlements under weeks or months of darkness. The 2018 dust storm that ended the Opportunity rover's mission lasted for several months and demonstrated just how dramatically Martian weather can affect technological systems designed to operate on the planet's surface. Let's begin our virtual geological tour at Olympus Mons, not just because it's the most famous Martian landmark, but because it represents the kind of geological extreme that defines Mars as a world where familiar processes operate on scales that are almost incomprehensible. Olympus Mons is the largest volcano in the solar system, a shield volcano that rises approximately 13.6 miles above the surrounding plain, nearly 3 times taller than Mount Everest and high enough that its peak extends well into Mars's thin upper atmosphere. But Olympus Mons isn't just tall, it's massive in every dimension. The volcano covers an area roughly the size of Arizona, with a base diameter of about 370 miles. To put this in perspective that's meaningful to human experience, if you were standing at the base of Olympus Mons, looking toward the summit, the peak would be beyond the horizon, lost in the curvature of the planet and the haze of the Martian atmosphere. The slopes are surprisingly gentle, only about 2 to 5 degrees in most places, which means that you could theoretically drive a vehicle from base to summit, though the journey would cover hundreds of miles and take you through dramatic changes in atmospheric pressure and temperature. The formation of Olympus Mons represents volcanic processes operating on timescales that challenge human comprehension. Unlike Earth's volcanoes, which are typically active for thousands or millions of years before becoming dormant, Olympus Mons likely grew continuously for hundreds of millions of years, fed by a persistent mantle plume beneath Mars's relatively stable crust. The absence of plate tectonics on Mars meant that the volcanic hotspot remained stationary relative to the surface, allowing lava to accumulate in a single location for geological ages, building up the massive structure we observe today. The gentle slopes of Olympus Mons are characteristic of shield volcanoes, which form when low-viscosity lava flows spread out over vast areas rather than building up steep-sided cones. On Earth, shield volcanoes like those in Hawaii are impressive, but Olympus Mons represents shield volcanism on a scale that's only possible on a planet with lower gravity and different atmospheric conditions. The reduced gravitational pull on Mars allowed volcanic structures to grow much taller than would be possible on Earth, where the weight of such massive structures would eventually cause them to collapse or subside into the planetary crust. But Olympus Mons isn't alone in its grandeur. It's part of the Tharsis volcanic region, a massive bulge on Mars's surface that hosts several other enormous shield volcanoes, including Arsia Mons, Pavonis Mons, and Ascraeus Mons. Together, these volcanoes represent billions of years of volcanic activity that fundamentally shaped not just the local geography, but the planet's entire surface topography, atmospheric composition, and rotational dynamics. The sheer mass of the Tharsis region is so enormous that it actually affects Mars's rotation, creating a planetary bulge that influences everything from seasonal atmospheric patterns to the flow direction of ancient rivers and the distribution of impact craters. The Tharsis region demonstrates how geological processes on Mars operate on planetary scales. The volcanism that created these massive structures wasn't just local mountain building. It was a process that reshaped the entire planet's surface and atmosphere. The volcanic outgassing associated with Tharsis volcanism likely contributed significant amounts of water vapor, carbon dioxide, and other gases to Mars's ancient atmosphere, potentially creating conditions that were much more favorable for liquid water and possibly life than the harsh environment we observe today. From the volcanic highlands of Tharsis, our geological tour would take us to Valles Marineris, a canyon system so vast and spectacular that it redefines our concept of what geological features can look like on planetary scales. Stretching over 2,500 miles across the Martian surface, roughly the distance from New York to Los Angeles, Valles Marineris isn't just a single canyon, but an entire system of interconnected chasms, valleys, and tributary channels that extends for about 1/5 of Mars's circumference. At its deepest point, Valles Marineris plunges more than 4 miles below the surrounding terrain, and in some places, the canyon system is over 120 miles wide. The Grand Canyon, impressive and beautiful as it is, could be tucked into one of Valles Marineris' smaller side canyons with room to spare. If Valles Marineris existed on Earth, it would stretch from San Francisco to New York, and you could lose several small countries in its depths. The formation of Valles Marineris remains one of Mars's greatest geological mysteries and represents processes that may have no direct analogue on Earth. Unlike the Grand Canyon, which was carved primarily by river erosion over millions of years, Valles Marineris appears to have been created by a complex combination of tectonic fracturing, volcanic activity, and subsequent erosion by wind, water, and possibly massive catastrophic floods. Some sections of the canyon system show clear evidence of layered sedimentary deposits, suggesting that parts of Valles Marineris may have once held lakes, inland seas, or even temporary oceans during periods when Mars's climate was warmer and wetter than it is today. The walls of Valles Marineris reveal billions of years of Martian geological history in cross-section, like reading the pages of a book that chronicles the planet's evolution from a potentially habitable world to the cold, dry desert we observe today. Different layers in the canyon walls represent different periods in Mars's history, including times when the climate may have been warm enough to support liquid water on the surface, and possibly even primitive life forms. These dramatic geological features aren't just impressive natural landmarks or subjects for spectacular photography from orbiting spacecraft. They're potential sites for human settlement, resource extraction, and scientific research that could unlock fundamental questions about planetary evolution and the possibility of life beyond Earth. The volcanic regions could provide access to mineral resources, geothermal energy sources, and protected locations for establishing human habitats. The deep canyon systems might offer protection from the intense radiation that reaches Mars's surface due to the planet's thin atmosphere and weak magnetic field, while also providing potential access to subsurface water, ice, and mineral deposits that accumulated over geological time. But these same geological features also represent significant hazards and challenges for colonists and mission planners. The dust storms that can originate in canyon systems like Valles Marineris can grow to encompass the entire planet, blocking sunlight for months and potentially stranding solar-powered equipment and human habitats. The steep canyon walls and unstable slope materials present obvious dangers for surface operations, while the extreme elevation differences create atmospheric pressure variations that complicate aircraft operations and atmospheric entry trajectories. And then there's 3E Atlas, our hypothetical interstellar visitor that represents a class of objects we're only beginning to understand, but which could fundamentally alter the trajectory of human space exploration. When astronomers first detected one, Oumuamua, in 2017, followed by two, Borisov in 2019, they opened a window into the startling reality that our solar system is constantly being visited by objects from other stellar systems, cosmic refugees carrying with them the chemical signatures, physical characteristics, and orbital dynamics of alien star systems light years away. These interstellar visitors are invaluable scientific targets that could teach us about planetary formation, stellar evolution, and the distribution of matter throughout our galaxy. But they're also potential threats to the carefully planned choreography of space missions that depend on predictable orbital mechanics and stable gravitational relationships. Every space mission to Mars involves calculations so precise that mission planners must account for the gravitational influence of every major body in the solar system, the pressure of solar radiation on spacecraft surfaces, and even relativistic effects that become significant over interplanetary distances. The gravitational modeling required to predict 3. Atlas's exact influence on the Mars system pushes our computational capabilities to their limits. Supercomputers at NASA, ESA, and other space agencies run millions of simulations, each testing slightly different parameters for the visitor's mass, composition, velocity, and trajectory. The results paint a complex picture of cascading gravitational effects that could ripple through the Mars system for decades after the visitor's passage. Even small changes in Mars' orbital velocity or the positions of its moons could have profound implications for mission planning, requiring spacecraft to adjust their approach trajectories, landing sequences, and departure windows. In our speculative scenario, 3I Atlas represents the kind of interstellar visitor that mission planners have nightmares about. One that arrives with a trajectory, mass, and timing that could disrupt decades of careful planning. Billions of dollars in investment, and potentially the safety of human crews already en route to or operating on Mars. Unlike the asteroids and comets native to our solar system, whose orbits we've mapped with extraordinary precision and can predict centuries in advance. Interstellar visitors come from the cosmic void with trajectories that are hyperbolic. They're traveling so fast that they're not gravitationally bound by our sun and will eventually continue their journey back to interstellar space. The velocities of these objects are part of what makes them so challenging to study and potentially dangerous to our carefully orchestrated space missions. When Oumuamua was detected in 2017, it was already traveling at about 196,000 miles per hour relative to the Sun, and it was accelerating as it approached perihelion, its closest point to our star. By the time it rounded the Sun and began its journey back toward interstellar space, it was moving at over 315,000 miles per hour. To put that speed in perspective, that's fast enough to travel from New York to Los Angeles in about 5 minutes, or to circle Earth's equator in less than 5 minutes. But raw speed isn't the only concern when dealing with interstellar visitors like our hypothetical 3I Atlas. These objects can vary tremendously in composition, size, internal structure, rotational state, and behavior as they interact with solar radiation and the solar wind. Oumuamua appeared to be a rocky, elongated object, roughly 1,300 feet long and perhaps 130 feet wide, with an unusual cigar or pancake-like shape, unlike anything we'd previously observed in our solar system. Its surface was dark and reddish, similar to the organic-rich materials found on some asteroids, but its behavior as it passed the Sun suggested internal characteristics that we still don't fully understand. Consider for a moment the intricate choreography required for any successful Mars mission, whether robotic or crewed. Every spacecraft sent to Mars must be launched during specific launch windows that occur approximately every 26 months, when Earth and Mars are properly aligned for the most efficient transfer trajectory. These launch windows aren't just suggestions. They're mandated by the physics of orbital mechanics and the limitations of current propulsion technology. Miss the optimal timing by even a few weeks, and your mission might require significantly more fuel, take much longer to reach Mars, or become impossible altogether given the constraints of spacecraft design and mission budgets. The precision required for Mars missions is almost beyond comprehension. Spacecraft must travel millions of miles through space, navigating through a complex gravitational field that includes the Sun, Earth, Mars, the Moon, and all the other planets, and arrive at Mars with pinpoint accuracy. The margin for error is often measured in kilometers and minutes after a journey lasting months and covering hundreds of millions of miles. Mission navigators must account for gravitational perturbations, solar radiation pressure, atmospheric drag during Earth departure, and a host of other factors that can affect spacecraft trajectory. The mathematics of interplanetary navigation involves solving what scientists call the n-body problem, predicting the motion of multiple objects under the influence of their mutual gravitational attraction. For Mars missions, This means accounting not just for the gravitational pull of Mars and Earth, but also the Sun, Jupiter, Venus, and even smaller bodies like asteroids that might slightly influence a spacecraft's trajectory over the months-long journey between worlds. The addition of an unpredictable interstellar visitor to this already complex equation introduces variables that could render years of careful mission planning obsolete. Now imagine that precisely choreographed dance being disrupted by the gravitational influence of an interstellar visitor whose mass, composition, and exact trajectory may not be fully known until it's already too late to make significant mission adjustments. Even small perturbations in Mars's orbit or the orbits of its moons could cascade into major problems for spacecraft attempting orbital insertion, landing sequences, or departure maneuvers. The challenge becomes exponentially more complex when you consider that these effects might not be immediately apparent. Subtle changes in orbital mechanics could take months or years to fully manifest, potentially affecting missions that haven't even been launched yet. 2I Borisov, in contrast, was clearly recognizable as a comet, with a visible coma and tail created by sublimating ice and dust as it approached the Sun. But even this more familiar-looking object presented surprises, with a chemical composition that differed significantly from comets native to our solar system, suggesting that planetary formation processes around other stars can produce very different results from what we observe in our own cosmic neighborhood. In our scenario, 3I Atlas represents something potentially more concerning than either of its predecessors. A larger object with a composition and behavior that could create significant gravitational perturbations as it passes through the inner solar system. The gravitational influence of such an object, even during a relatively brief flyby lasting only months, could have cascading effects throughout the Martian system that persist for years or even decades after the visitor has departed for interstellar space. Mars has two small, irregularly shaped moons, Phobos and Deimos, both of which are thought to be captured asteroids that were gravitationally snared by Mars at some point in the distant past. These moons are already in somewhat precarious orbits that are gradually evolving over geological time. Phobos, the larger and closer of the two, is slowly spiraling inward toward Mars due to tidal forces and will either crash into the planet or break apart to form a ring system within the next 50 million years. Deimos orbits farther out and is more stable, but its orbit is still subject to perturbations from the Sun, Jupiter, and other gravitational influences. A close passage by a massive interstellar visitor like 3I Atlas could potentially destabilize these already delicate orbital relationships in ways that might not be immediately apparent, but could accumulate over time into significant changes. Even small alterations in the Moon's orbits could affect spacecraft that depend on gravitational assistance from these bodies, communication satellites that use the moons as reference points for navigation, or future missions that might establish bases or mining operations on Phobos or Deimos. This brings us to one of the most fascinating and terrifying aspects of our speculative scenario: the interconnectedness of celestial mechanics and human ambition. In an age when space exploration has become not just a scientific endeavor, but a potential survival strategy for our species. When we plan missions to Mars today, We're not just planning for individual spacecraft and crews. We're planning for an entire ecosystem of support systems, communication networks, supply chains, and logistical infrastructure that depends on predictable orbital relationships and stable gravitational environments. The complexity of this interconnected system is staggering and represents one of humanity's greatest technological achievements. It includes Earth-based launch facilities, deep space communication networks, orbital transfer vehicles, Mars communication satellites, surface rovers and habitats, sample return systems, and eventually permanent human settlements with their own industrial capabilities. Every component of this system is designed around the assumption that the major gravitational influences in the Mars system will remain stable and predictable within well-understood parameters. The history of Mars exploration is a testament to human ingenuity, determination, and the willingness to learn from failure in pursuit of one of the most challenging goals our species has ever attempted. Our journey to understand and eventually inhabit Mars began in the early 1960s, during the height of the space race, when both the Soviet Union and the United States recognized that reaching Mars would represent the ultimate demonstration of technological supremacy and scientific achievement. The first attempts to reach Mars were ambitious but naive, reflecting our limited understanding of interplanetary travel and the harsh realities of space exploration. The Soviet Union's Mars 1M programs in 1960 never even made it out of Earth orbit due to launch failures, setting a pattern of costly setbacks that would characterize Mars exploration for decades to come. When the Soviet Mars 1 probe was launched in November 1962, it represented humanity's first successful departure from Earth orbit toward another planet. For several months, Mars 1 transmitted data as it traveled through interplanetary space, but contact was lost in March 1963, about 7 months into its journey and still millions of miles from its destination. The probe likely flew past Mars at a distance of about 120,000 miles, but without communication, it became just another piece of space debris in solar orbit. The American Mariner program began with similar frustrations. Mariner 1, intended to fly by Venus as a stepping stone toward Mars missions, was destroyed shortly after launch in July 1962 due to a guidance system error. But Mariner 2 successfully reached Venus in December 1962, proving that interplanetary travel was possible and providing valuable experience for future Mars missions. The breakthrough came with Mariner 4 in 1965, which became the first spacecraft to successfully fly by Mars and return close-up images of another planet's surface. The 22 grainy low-resolution photographs transmitted by Mariner 4 revolutionized our understanding of Mars and shattered many romantic notions about our planetary neighbor. Instead of the lush, potentially habitable world that science fiction had imagined, Mariner 4 revealed a cratered, apparently lifeless desert that looked more like the Moon than Earth. These early images were both disappointing and inspiring. Disappointing because they seemed to rule out the possibility of advanced Martian civilizations or obvious signs of life, but inspiring because they proved that humans could send sophisticated instruments across millions of miles of space and receive detailed scientific data from another world. The 1970s brought more ambitious missions and more sophisticated spacecraft. The Soviet Mars 2 and Mars 3 missions in 1971 included both orbiters and landers, representing the first attempts to actually land on the Martian surface. Mars 2's lander crashed, but Mars 3 achieved the first successful soft landing on Mars, though contact was lost just 20 seconds after touchdown, possibly due to a massive dust storm that was raging across the planet at the time. NASA's Mariner 9 orbiter, also launched in 1971, transformed our understanding of Mars from a static, moon-like world to a dynamic planet with evidence of ancient water activity, massive volcanoes, and complex geological processes. Mariner 9's images revealed Olympus Mons, Valles Marineris, and dried river channels that suggested Mars had once been much warmer and wetter than previously thought. The Viking missions of 1976 represented a quantum leap in Mars exploration technology and scientific ambition. Each Viking mission consisted of an orbiter and a lander, and both Viking 1 and Viking 2 successfully operated on the Martian surface for years beyond their planned mission lifetimes. The Viking landers conducted the first extensive chemical analysis of Martian soil, monitored weather patterns, and performed biological experiments designed to detect signs of microbial life. The Viking biological experiments returned tantalizingly ambiguous results that scientists are still debating today. Some chemical reactions in the Martian soil suggested possible biological activity, but the lack of organic compounds detected by other instruments made biological explanations seem unlikely. The Viking results highlighted both the challenges of searching for life on other worlds and the importance of conducting multiple types of experiments to avoid misinterpreting complex chemical processes. The Viking biological experiments, though inconclusive, established methodologies and protocols that continue to influence the search for life on Mars today. The experiments tested Martian soil for signs of metabolic activity, photosynthesis, and organic compounds using techniques that were revolutionary for their time. While the results were ambiguous and continue to be debated, they provided crucial data about Martian soil chemistry and established the importance of conducting multiple, complementary experiments when searching for signs of life in extreme environments. After the success of Viking, Mars exploration entered a challenging period marked by several high-profile failures that demonstrated just how difficult interplanetary missions can be. The Soviet Phobos missions of the late 1980s were intended to study Mars and its moon Phobos, but both spacecraft were lost due to technical failures. NASA's Mars Observer, launched in 1992 with sophisticated instruments for studying Martian climate and geology, was lost just before arriving at Mars, possibly due to an explosion during propulsion system pressurization. The 1990s brought a new approach to Mars exploration, emphasizing smaller, less expensive missions that could be launched more frequently and with less catastrophic consequences if individual missions failed. NASA's faster, better, cheaper philosophy led to missions like Mars Pathfinder, which successfully landed on Mars in 1997 and deployed the first successful Mars rover, Sojourner. Spirit and Opportunity proved that ancient Mars was much warmer and wetter than the frozen desert we see today, discovering evidence of past water activity in rocks, minerals, and geological formations. These discoveries established Mars as a potentially habitable world during its early history and made the search for signs of past or present life a central focus of Mars exploration. The Mars Science Laboratory mission, which landed the Curiosity rover in 2012, represented another major advancement in Mars exploration technology and scientific capability. Curiosity is the size of a small car and carries a sophisticated chemical laboratory capable of analyzing rock and soil samples with unprecedented precision. The rover has discovered evidence of ancient habitable environments, seasonal variations in atmospheric methane that might indicate biological activity, and complex organic compounds that provide important clues about Mars's chemical evolution. The challenges revealed by this history of Mars exploration provide important context for understanding what 3I Atlas could mean for future missions. Every successful mission to Mars has required precise navigation, careful timing, and the ability to operate sophisticated equipment in one of the most challenging environments in the solar system. Even small changes in orbital mechanics, atmospheric conditions, or the gravitational environment could have cascading effects on mission success. Looking toward the future, the challenges become even more complex as we transition from robotic exploration to human presence on Mars. The first crewed missions to Mars will require life support systems, landing capabilities, surface habitats, and return vehicles that are far more complex and vulnerable to environmental changes than anything we've previously sent to Mars. Current plans for Mars colonization involve establishing permanent human settlements that can eventually become self-sufficient, reducing dependence on supplies from Earth, and creating backup locations for human civilization in case of global catastrophes on our home planet. These settlements would require massive infrastructure projects, including power generation systems, manufacturing facilities, agricultural systems, and communication networks that all depend on predictable environmental conditions and stable orbital relationships. The international cooperation required for successful Mars colonization adds another layer of complexity to the challenge. No single nation has the resources or technical capabilities to establish a permanent human presence on Mars independently, which means that Mars exploration and colonization will require unprecedented levels of international cooperation and coordination. This cooperation must be sustained through geopolitical tensions, economic competition, and changing national priorities over the decades required to establish sustainable settlements. The potential for an interstellar visitor like 3I/Atlas to disrupt these carefully laid plans highlights the fundamental challenge of long-term space exploration. We're attempting to establish human civilization on other worlds in a universe that is dynamic, unpredictable, and occasionally hostile to our best-laid plans. The gravitational perturbations, atmospheric changes, or orbital disruptions caused by such a visitor could affect not just individual missions, but the entire trajectory of human expansion into the solar system. But perhaps the most profound implications of our speculative scenario involve the broader questions about humanity's relationship with the cosmos and our place in the universe. The possibility that an interstellar visitor could threaten our expansion to Mars forces us to confront fundamental questions about the nature of exploration, discovery, and human resilience in the face of cosmic uncertainty. Throughout human history, exploration has always involved accepting risks and uncertainty in pursuit of knowledge, resources, or new homes. From the first humans who left Africa to populate the globe, to the Polynesian navigators who crossed thousands of miles of open ocean to discover new islands, to the European explorers who crossed oceans to reach new continents, human expansion has always required courage in the face of the unknown. Space exploration represents the ultimate extension of this human drive to explore and expand, but it also represents exploration in an environment where the stakes are higher and the margin for error smaller than ever before. The harsh realities of space travel and planetary settlement mean that mistakes that might be survivable or recoverable on Earth could be fatal in space, where there's no breathable atmosphere, no accessible food or water, and no immediate possibility of rescue. The potential threat represented by 3I Atlas in our scenario serves as a reminder that the universe is not a passive backdrop for human ambition, but an active, dynamic system where unexpected events can have far-reaching consequences. This doesn't mean that we should abandon our dreams of becoming a multi-planetary species, but rather that we need to approach space exploration with appropriate humility, careful planning, and the flexibility to adapt to unexpected challenges. The infrastructure required for Mars colonization represents one of the most complex engineering challenges humans have ever attempted, involving systems that must operate reliably for decades in an environment where replacement parts and technical support from Earth may be months or years away. Every component, from solar panels and nuclear reactors to life support systems and food production facilities, must be designed to withstand the unique challenges of the Martian environment, while maintaining the precise operational parameters necessary for human survival. The life support systems required for Mars colonization must operate with a level of reliability that exceeds anything achieved in human technology. Unlike the International Space Station, where emergency evacuation to Earth is possible within hours, Mars colonists would be committed to their artificial environment for years at a time. Every component, from air recycling systems to water purification equipment to food production facilities, must be designed with multiple redundancies and the capability for in situ repair and replacement using materials available on Mars. Consider the psychological and social implications of Mars colonization in the context of potential threats like 3I/Atlas. The first Mars colonists will be completely dependent on their technology and infrastructure for survival in ways that have no parallel in human history. Even temporary disruptions to power systems, communication networks, or life support could be fatal. And the isolation from Earth means that help is at best months away, and more likely years. The economic implications of Mars colonization are equally staggering and complex. Current estimates for establishing a permanent human presence on Mars range from hundreds of billions to trillions of dollars, representing investments that dwarf any previous human endeavor. These investments must be sustained over decades through changing political administrations, economic fluctuations, and potential global crises on Earth. The financial models for Mars colonization assume sustained investment over decades, requiring economic frameworks that can survive political changes, market fluctuations, and competing priorities on Earth. Some economists argue that Mars colonization could become economically self-sustaining through the export of rare minerals, scientific discoveries, or technological innovations developed specifically for the Martian environment. Others contend that the costs will always exceed any potential economic returns, making Mars colonization essentially a form of cosmic insurance policy for human civilization. Pathfinder and Sojourner captured public imagination in ways that previous missions had not, partly because they landed during the early days of widespread internet access, allowing people around the world to follow the mission in real time through NASA's website. The images of Sojourner's small wheels rolling across the Martian surface brought the reality of Mars exploration into homes and classrooms, inspiring a new generation of scientists and engineers. However, the faster, better, cheaper approach also led to some spectacular failures. The Mars Climate Orbiter was lost in 1999 due to a navigation error caused by confusion between metric and imperial units, a mistake that cost $327 million and highlighted the importance of rigorous quality control in space missions. The Mars Polar Lander, also lost in 1999, likely crashed due to a software error that shut down its engines prematurely during landing. Each failed mission taught invaluable lessons that contributed to the success of future endeavors. The loss of the Mars Climate Orbiter in 1999, caused by a simple unit conversion error, led to the implementation of rigorous verification protocols and standardized measurement systems across all international space missions. The premature shutdown of the Mars Polar Lander's engines, likely caused by vibrations being misinterpreted as ground contact, resulted in more sophisticated landing systems and redundant sensor arrays that have made subsequent landings more reliable and precise. The early 2000s marked the beginning of the modern era of Mars exploration, characterized by increasingly sophisticated rovers and orbiters that have fundamentally transformed our understanding of Martian geology, climate history, and potential for life. The Mars exploration rovers Spirit and Opportunity, launched in 2003, were designed for 90-day missions but operated for years, with Opportunity continuing to function for nearly 15 years until it was finally silenced by a planet-wide dust storm in 2018. The philosophical implications of becoming a multi-planetary species extend far beyond simple survival strategies. When humans establish permanent settlements on Mars, we will fundamentally alter our relationship with Earth and our conception of what it means to be human. Martian colonists will develop their own cultures, traditions, and perhaps even evolutionary adaptations to their environment. Over generations, the descendants of Earth-born colonists may come to think of Mars as their true home, viewing Earth as an ancestral homeland rather than the center of human civilization. The answer to these questions may determine not just the success of human expansion to Mars, but our long-term survival as a species in a universe that is far more complex and dynamic than our ancestors could have imagined. The challenges represented by scenarios like 3i Atlas may ultimately make us stronger and more adaptable, forcing us to develop the technological capabilities, international cooperation, and philosophical frameworks necessary to thrive as a truly cosmic civilization. The challenges posed by potential cosmic threats like 3I Atlas may ultimately strengthen our species' capacity for long-term survival and adaptation. By forcing us to develop more flexible mission planning, more robust technological systems, and more sophisticated international cooperation frameworks, such challenges could accelerate our development into a truly spacefaring civilization, capable of thriving in the dynamic, unpredictable environment of the cosmos. The universe may be testing our readiness to join the cosmic community of spacefaring civilizations. As we stand on the threshold of becoming a multi-planetary species, we face challenges and opportunities that will define the future of human civilization for centuries to come. The potential threats represented by interstellar visitors like our hypothetical 3I Atlas remind us that space exploration is not just about developing better rockets and life support systems, but about preparing humanity for a future where we must learn to thrive in a dynamic, unpredictable universe. The scientific value of studying interstellar visitors like 3I Atlas cannot be overstated, regardless of their potential impact on human space exploration. These objects carry with them information about stellar systems light years away, providing insights into planetary formation, stellar evolution, and the distribution of matter throughout our galaxy. They represent natural laboratories that bring cosmic processes directly to our solar system for study. Understanding the composition, structure, and behavior of interstellar objects could provide crucial insights into the conditions that exist around other stars and the processes that might have influenced the formation of our own solar system billions of years ago. This knowledge is essential for understanding our place in the universe and for making informed decisions about the search for life beyond Earth. The technological challenges posed by potential threats, like 3I Atlas, could also drive innovations that benefit space exploration more broadly. Developing better detection systems for interstellar objects, creating more flexible mission planning tools, and designing spacecraft that can adapt to changing conditions could all enhance our capabilities for exploring and eventually settling other worlds. From a philosophical perspective, the possibility of cosmic threats to human expansion forces us to consider what it really means to be a spacefaring civilization. Is our goal simply to replicate Earth-like conditions on other worlds, creating isolated outposts of human civilization scattered across the solar system? Or should we be developing the capabilities and mindset necessary to thrive in a dynamic cosmic environment where unexpected challenges are part of the normal experience? The story we've explored today, the potential impact of an interstellar visitor on human expansion to Mars, is ultimately a story about resilience, adaptability, and the human spirit of exploration in the face of cosmic uncertainty. Whether or not we ever encounter a real 3I Atlas, the exercise of thinking through such scenarios prepares us for the real challenges we will face as we expand beyond Earth. The universe is vast, ancient, and full of wonders and threats that we're only beginning to understand. Our journey to Mars and beyond will require not just advanced technology and international cooperation, but the wisdom to remain humble in the face of cosmic forces far beyond our control. and the courage to continue exploring even when the universe reminds us how small and fragile we are in the cosmic scheme. In the end, the greatest threat to human expansion into space may not be any particular cosmic visitor or environmental hazard, but our own failure to maintain the vision, commitment, and international cooperation necessary to sustain such an ambitious endeavor over the decades and centuries required to establish permanent human settlements beyond Earth. The cosmos has been sending us visitors from beyond our solar system for billions of years, most of which we never noticed and which had no impact on Earth or human civilization. The detection of interstellar objects like Oumuamua and Borisov represents not a new threat, but a new awareness of the dynamic environment in which our solar system exists. This awareness should inspire us to become better prepared for the unexpected, more flexible in our planning, and more committed to the long-term vision of human expansion into the cosmos. As we conclude this speculative journey through the potential impact of 3 IA Atlas on Mars exploration, remember that the real exploration of Mars continues every day through the work of thousands of scientists, engineers, and mission planners around the world. Every image returned by Mars rovers, every data point collected by orbiting spacecraft, and every successful technology demonstration brings us closer to the day when humans will walk on the surface of another world and begin the next chapter in the story of human civilization. The challenges are real, the risks are significant, and the uncertainties are substantial. But the potential rewards for science, for human knowledge, and for the long-term survival of our species make the effort not just worthwhile, but essential. Whether we face cosmic visitors like 3I Atlas or entirely different challenges we haven't yet imagined, humanity's future among the stars depends on our ability to remain curious, adaptable, and committed to the greatest adventure our species has ever undertaken. The red planet awaits, the cosmos watches, and the future of human civilization hangs in the balance of decisions we make today about our commitment to exploring and eventually inhabiting other worlds. In the vast sweep of cosmic time, we are writing just the first few pages of what could be an epic story of human expansion across the galaxy. Or we may be recording one of the final chapters of a species that couldn't quite manage to escape the confines of its birth world. The choice and the responsibility belongs to all of us.